I'm going to show you an example here to demonstrate reflecting a point in a plane. So here's the question. We've got a plane there and we've got a point here A, and what we've got to do is find the coordinates of a point on the other side of the plane, so when it's been reflected. Now, this question is nicely set up. It's not just given to you like that. There's a little bit of work to do, and it involves finding a line that goes through the plane and through the point, and therefore being able to find this point here, and then from that you can work backwards to find this point here, the reflection A dash. Now then, a couple of options here. What I'd really strongly recommend you do is you pause the video right now and just have a go at that yourselves. If you don't stop the video, I'll go through it and you can follow it step by step. Okay, I'm going to start that now, so pause the video if you want to try it yourselves. Right then, so the first part of this is we've got to find the equation of the line, the Cartesian form. So what is the line? Well, the line L, as we're given there, goes through this point 2, 5, minus 1, and it's perpendicular to the plane. Okay, so that's our Cartesian equation of the plane there, and that's useful of course for giving us the direction of the normal. Well, if the direction of the normal is 1, 1, 1, then the direction of the line is going to be 1, 1, 1 as well. So the equation of the line, well, that's very easy if we want it in vector format there, because we've got a point on the line, 2, 5, minus 1, and we've got a direction which is 1, 1, 1. So very simply we can write the equation of the line is equal to 2, 5, minus 1 plus lambda 1, 1, 1. Now let's just go back to the question. It does actually ask us for the Cartesian equation of that line, so we just need to rearrange it. We could write R is x, y, and z, so we can have x is equal to 2 plus lambda, y is equal to 5 plus lambda, and z is equal to minus 1 plus lambda. And so if we want the Cartesian form, we just need to rearrange these equations. So we've got lambda, so lambda is equal to x minus 2, it's equal to y minus 5, and it's equal to z plus 1. So that is the Cartesian form of the equation of this line L. Right, that's that done. Second part, find the point of intersection of the line and the plane. So what we're asked for here is this point. I'm going to call that B, a point that is in the plane and on the line. So the intersection of the two. And you might remember a method for doing that. And the method I'm going to use is just to find the intersection of those by substituting the values of x for the line into the equation of the plane. So x we know is 2 plus lambda, we've got y which is 5 plus lambda, and z is minus 1 plus lambda. Well, if we subtract 1 from that we should get 0, which gives me a value eventually of lambda is equal to minus 5 over 3. With that sort of value there, I'm a little bit suspicious I haven't made a mistake. Quite often the values that you get for these parameters are whole numbers, so I've just stuck that into autograph there just to check that, and it seems actually that point there it does make sense, so I don't think I've made a mistake. So that's the value of lambda that will make the position of the line or a point on the line and be the same as a point on the plane, and all we've got to do is substitute those values into here. So the x value is going to be 2 plus lambda, so that is 1/3. The y coordinate is 5 plus lambda, which is 3 and a third, and the z coordinate is minus 3 and a third. So that's going to be the coordinates of my point B, which is the intersection of the line and the plane. And the last part of the question, and this is the key part really, is to find this point A, the reflection of A, sorry, on the other side of the plane. So I was getting a bit busy there, so let's just redraw that. I've got my plane here, I've got a point on one side of the plane, and I've now worked out the coordinates of this point in the plane on that line, and this is the one I'm after. And it's actually a very, very simple question now when you consider that, provided you understand what's going on. Because since this line here is the normal to the plane, then this line on the other side here is also going to be the normal to the plane. So that means the line A to A dash is a straight line that passes straight through B. So what does that mean? Well, it means that the movement that we have from A to B, that vector will be exactly the same vector as from B to A dash. So you should be able to use that to work out the new position of A, or the reflection of A. So the x coordinates change from 2 to 1/3, so we've subtracted 5/3. We need to subtract another 5/3 there, so the x coordinate of A dash is going to be minus 4/3. Do the same for the y coordinate. We've subtracted 5/3 there, so we need to subtract another 5/3, which gives us 1 2/3. From minus 1 to minus 3 1/3, we've taken off minus 5/3, and we've got to take off another 5/3. Actually, I'm just looking at this y coordinate here. I can see I've made a mistake there. Just coming back to this, the z coordinate is minus 1 plus lambda, which is minus 2 2/3. So obviously that's wrong, a little bit wrong there. Minus 2 2/3, and we need to subtract the same amount, therefore, so we get a z coordinate of minus 4 1/3. Okay, so that's the method that we might use for that type of question. We're trying to find the coordinates of a point when it's been reflected in a plane.